Welcome everybody to our tutorial today. It's a family meeting.
Kind of, sort of.
Kind of, sort of. We're really happy to have all of you here. So the title of this tutorial is about reproducibility in database systems research revisited, because there have been great tutorials on this topic years ago. I'll get to that. Nullius in Verba, the first title of our tutorial, is inspired by the Royal Society motto, where it's been stated that it's all about the determination to verify all statements by an appeal to facts that are determined by experiment. So you need to show the facts and the experiments, and this is what this tutorial is about. So we will briefly introduce ourselves.
So I'm happy to present this tutorial with my esteemed colleague Stefanie Scherzinger from the University of Passau, who's been a software developer at Google and IBM in her earlier life.
And I introduce Wolfgang Mauerer with a dual career, both in industry, Siemens corporate research, and in academia. He's a professor at the Technical University of Applied Sciences in Regensburg.
And that is how you prepare a tutorial in these days. So just in case you're wondering, while we're here with less than 1.50 meter distance between us, we are continually testing ourselves. And if we believe that C stands for control and not for corona, we should be safe for the time being.
Yes, so for the reproducibility, of course, is very important in any science. But especially in computer science, we've seen a large shift in the standard that has been raised in how you do experiments. So there was a lot of foundational work, in particular, in the data management community. So a seminal paper was from Sigma 2008, the repeatability experiment, where they tried to verify the results that have been published. Then just last year, the Sigma community awarded leaders in the field for their contributions to repeatability and experimental design. And many of you will be familiar with those Sigma reproducibility badges that you see on the lower left in the figure, where published papers can be awarded for being repeatable. Now we're building on top of this foundational work, but in this tutorial today, we're showing you gold standard techniques for packaging your research artifacts, and it's going to be quite hands-on, really. So we'll talk about Git and GitHub. We'll talk about an initiative called Reproducible Builds. You'll see a lot of Docker, and we also show you where you can host your research results and where you can get a document object identifier that lets you find all your data and research artifacts online.
Basically everything that should have been expected during the last 50 years in research, but hasn't.
So our tutorial is heavily inspired by what we can observe in industry. Industry is really good at designing for long-term maintenance. If you think about Boeing, the 747 aircraft, the development started in 1966. The last machines are scheduled to be produced in 2022, so next year, and they will be in service until about 2050. So we are looking at a whole century of engineering where you need to document and maintain all this hardware and all this software. Similar achievements are made in Bitcoin, in programming for Bitcoin, or in the Tor browser, where you really want to make sure that the code you compile is really what you want to compile and that nobody has tampered with it. And the civil infrastructure platform, Wolfgang, maybe that's something you want to talk about.
Yeah, that's one initiative that's very dear to my heart, because I founded it in industry. It's a consortium of various major users and contributors to the Linux kernel. So our goal is to supply industry with Linux kernels that are supported for at least 10 years, 10, 15, 20 years, which is nothing compared to the lifetime of a typical industrial appliance, but is necessary these days because you don't want to let your power station get out of the grid because the kernel doesn't update anymore. You don't want to replace your trains every 10 years because you need to move from Linux to Mac OS to Windows to whatnot. And here we have the same requirements as in reproducible scientific experiments. We need to make sure that we can build the stuff we did 10 years ago, we did 15 years ago, in the exact same way as we did back then. Especially when it comes to certified devices in the medical sector, magnetic resonance tomographs, and so on. So there's lots of work already going on in industry with the result of making things reproducible, with the result of making things long-term available. And that is why our strategy for research is not to reinvent the wheel, as we often do, but to piggyback on what industry already provides for us. There's lots of tools, there's lots of open source tools in particular that just wait to be used and solve exactly the problem that we are facing in science. And since it's since we have a reproducibility crisis, one could even say in many fields of science, from psychology to including computer science, we find it's high time to really make use of what is offered by us to us by open source and by the communities.
So let us give you a brief rundown of what we're planning for this tutorial. So we'll present a working example that will carry us throughout the tutorial. Then we'll review some basics on reproduction. So what are the goals? How do you build and compare artifacts? Then we'll deeply focus onto Docker. So how to build proper reproduction images with Docker and how to design for reproducibility when you're doing your research. In particular, we show you that Git can do much more than just version your code. You can actually make it tell stories and retell stories. We'll briefly talk about licensing considerations, and then we'll show you an end-to-end reproduction live of using our Docker image. And then it's already time to wrap up. If you want to join us, here's a GitHub link. It's actually listed on the bottom of each slide. And you can actually have the Docker image build in the background while we're warming up.
Don't look at it too closely though yet. We will be cleaning that up over the next couple of days to send out some rough presentational edges that may still be in there, which has nothing to do that we always finish stuff just on time. And as of finishing stuff just on time, what we will show you will cost you more effort in the beginning when you do your research, when you do your publications, but we can also definitely promise you that in the long run, it'll save you work much more than you've initially invested.
So this is our research project. So we actually believe that the world of databases should be much more polite. Anyway, we all should be much more polite to each other.
Yeah, there's not enough love in this planet.
And we want to fix this. So we're building a version of SQLite that we call SQL Polite. And you have to always ask to please select something from the database. Now, if you forget the please, there's a 25% chance that the database will be upset. It will remind you to be more polite. And
so it'll punish you to be more polite.
And it will introduce a penalty, a latency overhead, and make you wait a bit because you were not polite. Yeah? And we hope that this is going to improve friendliness in the database world. So we're building SQL Polite based on SQLite. We actually have also an extra feature called a Pretty Please that will show you later on what we mean with that. So we're adding an extra feature there also. And as researchers, we want to evaluate our work. So there are two things we need to do. First of all, we want to measure various kinds of time measurements with the TPCH benchmark. I mean, what else? We're database people. So we want to measure latency, throughput, query runtimes. And then we also have to establish that the query results are correct. And when comparing database query results, you need to make sure the results are at least equivalent. Yeah, there may be differences due to ordering that you have to account for. So that's also something we have to do.
And since I'm not a database person, but an open source person, we of course use lots of existing code from the open source world, which is also quite common in database research these days, as I hear. But we also structure everything so that we can actually also contribute things back that are not just relevant for our research, but maybe for a larger audience, maybe even for commercial users. And also show how to properly maintain things during the research process and how to make your life easier by structuring your work in a way that you can benefit from what's actually happening in the upstream repositories in the development of SQLite and other packages that we base our work on.
So let me spend some more words on this, because what do we have that needs packaging, right? We have our SQLite version, the SQLite that we built with GCC. We have to take care of TPCH. So what's there that we're reusing? So we're taking the SQLite GitHub repository, we're forking from it. We have our own fork that we keep continuing to work on. We have one repository where we keep all our scripts and evaluation code in there. And then we also make use of two further repositories that provide us with a SQLite version of the TPCH data and a script to actually load that data into SQLite. So already we have all kinds of artifacts here that need management and that need packaging. Okay, so let's first look at the things we want to measure. Now, mind you that this tutorial is not on experimental design. That's not our main focus. There have been fantastic tutorials at ICDE in earlier years on just that. But we will do a little bit of standard measurement. So we measure the runtime of the queries, the throughput, their latency, and of course, we will encounter noise and variability. That's inevitable. And that makes it difficult to actually compare results.
Yeah, even with our simplified example, so although we're not targeting DB2 on S390 mainframes, we basically have everything that you should have included in the typical database research endeavor. And that's why we think our reproduction image that we provide to you, this scenario that we've created, is a really good fit to adapt it to your own needs, or to adapt it if you happen to write a bachelor master's thesis, if you happen to write a student paper, things like that. You will have a starting point that will also reduce your overhead to get into reproducibility.
So here you see an excerpt of a C program where we're measuring latencies. Yeah? So we're allocating a main memory buffer, we're recording timestamps, we're running the query a certain number of times, and then we're computing the time differences and write those to standard out. So nothing unusual here. Yes, we would do quite the similar thing if we were working with Java, but since SQLite or SQPolite is written in C, it makes sense to make the measurements in C here as well. What's special in the database context is that the build environment that we have to build our database, to build and develop the test scripts is not the same environment as where we might want to run the experiments. And that is something that we will show you a strategy on how that can be done. What you see here is not on measuring, this is on comparing query results for correctness. And that's an extension we wrote for SQPolite. You can load a special package called Pretty Please, and then you can ask the database to select Pretty Please, the comment from the TPCH orders. And since we didn't ask it to please select, the database is going to complain in 25% of the cases, what was the magic word again? So it's being strict with us. In this case, we're going to get a delay on the, like we said, on the query answer. And what the Pretty Please does is that it randomly injects please requests into text whenever you're at the end of a sentence. So if we execute Pretty Please in sequence twice, we don't get the exact same query result, because here the please was inserted in the third tuple. Here it was inserted in the second tuple. Yes. Why are we doing this? What's the idea behind this? Well, often when you're checking the results that you get back from a database engine, there is this kind of variation, often caused by parallelisms or other random effects that you get. Just think about comparing the results of parallel MapReduce jobs. So you need to often write custom code to ensure that the query results are equivalent, even though they may not be identical. And this static example mimics that. Okay.
Yeah, we have it all. So we have some artifacts that we need to build, some non-trivial ones based on existing code, based on research extensions to this very code, based on external modules that could also work, or that could also be structured like with proprietary systems where you cannot modify the source code, like with Oracle's database, with DB2 and so on. We have a non-straightforward build process, so we require a fair amount of external dependencies. We also do the data processing in the reproducibility image that requires a lot of statistical software, a lot of plotting packages, and so on. And we need to do comparisons on the artifacts that we generated, binaries, and so on, and the results that we created. Now let's just look at the chat, because there have been some questions on the chat here. Oh, Michael Flut asked, the repository is not visible yet. Yeah, that's indeed true. Ralph, please wait setting that to visible. I'd still like to make a change or two before we can really publish that. So let's call that a feature, not a bug. But we will eventually publish that. And we'll show you everything in the tutorial that you need so far. Good. So what do we need to deal with? Basically, it's two types of things that need to be reproduced. It's the artifacts, the code, the binary code that's generated by the compiler. It's fairly easy to establish that the sources are unchanged. You all know how to do that. But when you run these sources through a compiler, you want to make sure that the compiler generates exactly what you got 10, 15 years ago, or what the PhD colleague in the next room got, because you don't want to introduce any variability that way. Thankfully, we can make sure by checking for bitwise identity that binaries are really the same. That's not so easy with any observables. We know that from physics, when you measure things like time, energy consumption, whatnot. Same thing for databases. When you measure execution times or energy consumptions, you will have variations caused by some unavoidable tasks that run on your machines, by some internal noise in the machines, and so on. We have functional results, like the results of a select query, that are basically checkable bitwise identical, but can also be need to be checked permutation-wise, like in the please example, or when the database reorders things. And we can also have stochastic results, like when you do plots, when you do numerical post-processing, and so on, with uncontrollable random numerical noise. There's a number of more questions that we don't discuss in this tutorial. For instance, in systems engineering, you're often required to build tool chains yourself from scratch. That would also be the gold standard in databases. You could start with the tool chain in source form, build that, rebuild that. If you are Ken Thompson and got an ACM Turing Award for trusting trust, you may do that. It's always the question, how far would we go? So we don't go that way. We trust the distributions to give us proper binaries, same for unspecified dependencies and external sources. So even if we cover a lot of ground, we don't cover everything. And let's start with the first hands-on example, namely building and comparing binary artifacts. I will start with a very simple example, which already shows you that the problem at hand is quite complicated. We're not going to talk about linking. We're not going to talk about handling libraries. We're not going to talk about handling other languages like Java, C#, and so on. Just use plain C and give you an idea where the problems are. So let me move to a... So you should all be seeing a terminal, do you?
Yes.
Yes. Okay, great. So we have an example, and you may know that from your Programming 101 course, a Hello World example, not quite fascinating, not quite complicated. We say printf hello ICDE, and that's it. Of course, you know all how to compile that. Use GCC, include debug information, because you also all know that writing code is harder than how we can think. So we will introduce bugs, and we create a binary hello. And that hello binary does, what it's supposed to do. It says hello ICDE. Great thing. Now, assume I compiled that in 1990. And how do I prove to you, or how do I tell you what the result of that compiled process was? I give you a SHA-SUM, SHA-256, for instance. So we have this SHA-SUM. Let's just remember that. And if I build the same thing again with the same compiler on the same system, then not too much surprise. This is nothing that goes without saying that it's obvious. There are cases where even such a compile can give different results, but for this very simple example, it's the same. Okay, now we did that on a we did that in a certain directory. Now let's move to another build directory and build the exact same binary from the exact same sources again. Okay, I need to take my sources now from directory up one level in the hierarchy, but it's the same thing. Says the same message. And surprise, surprise, now the SHA-SUM is different. So although we've worked on the same machine, we use the same compiler, we use the same user, we use the same sources, we already, for this very simple example, get unreproducible differences. That's something that should let your alarm bells ring. Question is how come? How could that be that there are differences? And there's thankfully a lot of tools available. We would like to show you a tool that's called Diffoscope. You can guess from the name, it's about finding differences in binaries. It cannot just handle C, it can handle Java jar files, it can handle PDFs, it can handle websites, it can handle source code, can handle everything up to toasters. And let's give that the two examples that we built. It does its magic, and then you see, okay, it has a lot of differences. Now, without going into the details, when you scroll through that carefully, you will see here minus plus lines are typical diff format, what has changed. And you see the debug mode has inserted absolute file names into the binary. And these absolute file names obviously change depending on where you build the thing, which is a pretty typical source of unreproducibility, because the PhD next to you usually has a different username, a different home folder than yourself. And that already gives you differences. Okay, so we could probably try to say, yeah, I want my debug information, but when I distribute the binaries, let me strip off that debug information. I do that for both binaries, compare them again, and see, yeah, differences are now less, but even for that, even if I removed all this information, I may still have different build IDs encoded in the files. That's a pretty minor difference if you know that this is the only difference, but it requires you to know where the difference is. And that's obviously something that's inconvenient when you want to check identity for large projects for tens of thousands.
Trouble behaviors, which include...
Pardon me if that was a question, I didn't hear it. But you may, of course, feel free to interrupt us anytime.
I think that was from.
Okay, that was just some noise we heard. Okay,
good.
Good. So already for that simple example, it fails. Let me very quickly present another one. Even if we decide to build in fully reproducible mode, so without debug information, without anything, we can decide it's now time to move on with our research, and we want to use a logging library because printf is so 70s, so we don't use printf to output our log messages. The log library also handles when we need to insert new lines and since the log library has a built-in function to report its version, we can also build that into the code. So we say using logger %s, and then that the system, the get info is also defined in log.h. Let that give us the logging information, which is also a fairly common pattern that programs do. They use a library, they report the version of the library used. Everyone who has ever said PDF LaTeX -- version knows that programs like to announce their own version. So let's compile that once. Of course, I now need to include the library into my compile and compute a SHA-SUM. For hello, this is what we get. We have a super duper code that prints the version of the log library and hello ICDE. And you can already see the smell here. The log library inserts the build timestamp, which is something that software also likes to do quite a lot. And when I build again, I get nearly same output, but different build date. And of course, that implies a different char sum. For now, it's fairly obvious why we got the differences. But again, imagine you're building a huge project with thousands of C files, and to pin down these mirrors to one file is quite a lot of work. Without going into more details, what we'd like to show you, or what we'd like to advise you, is to take a look at this project here, the reproducible builds effort. That's actually one of the industrial efforts that we mentioned. It's a number of people in Debian that are, by the way, also funded by the civil infrastructure platform I mentioned earlier, because this is a really important problem for us, that lists a number of measures how builds can go wrong, ranging from fixing the date epoch in builds to some value so that you avoid these time date things, different time zones in builds, version information, order of inputs, lots and lots of things. So much more than we can cover in this tutorial. What we'd like to show you nonetheless is a tool called Repro Test for reproducibility test. It's basically a magic knife that's deliberately not included in the standard image that we give you because it pulls in 1.6 gigabytes worth of dependencies, but which fairly easy allows you to test if any build is reproducible or not. Usually you would have a build system like make or whatnot, or CMake or bitbake, things like that. I can also directly use it with the compiler command line. I can tell the repro test, please use this command to build the result, and then hello is the resulting artifact that must be identical across all these variations, and then the tool goes away and tries systematically all these variations and gives you a report in the end of the day that then marks the differences. And so here you see, of course, date is already one thing that's suspicious. And here we already know that this comes from debug builds run in different directories. Again, without going into details, that's the tool you want to use. You have your research code, you run repro test on that, and it tells you where things can go wrong and where not. Yeah, as you see, we didn't even talk much about linking, file order in linkers, libraries, tables, blah, 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 blah. But these two tools are worth their weight, 0 grams in gold, and maybe even more. And we'll all list them on the accompanying websites.
So the goal is, what you want to achieve is that you create an island of stability in an ocean of activity. You want to be ideally completely independent of any updates to external components, yeah, because things around you change. The base system details change, package versions change over time, the system runtime configuration. We've encountered ourselves that within just a few years, GitHub repositories disappear or projects move between hosts. So projects that 10 years ago were hosted on SourceForge are now on GitHub.
Think about 1966. What repositories did Boeing use for their Algol 60 code and their COBOL code?
And if you rely on external software, it may no longer be maintained, download links disappear. So things happen. Yeah? So the ultimate goal is to be self-reliant and self-contained. You want to have a complete environment where you can build your stuff even when you're trapped on an island without internet, or just 20 years after all the repositories have gone.
Yeah, we're of course assuming that you have a computer on your island. Without one, it's going to be quite impossible. It's not completely impossible, but it's very hard. So the workflow that we suggest, and just to mind you for the slide before, that's all on top of a reproducible build that you do from your static local configuration. You first need to figure out how to do that build reproducibly. Then you have to solve all these issues on top. And here Docker comes into play, another solution that industry came up for many, many different problems, including reproducibility. What we will show you is basically an example of a Docker container that takes various inputs, public Git repositories, patches that come into the repositories. It can also handle binaries. It can handle build recipes. We all unite these in the container. We pull these dependencies in from the internet, from various links. Once they're here, we save them also. We cut off we can cut off connectivity completely, and then we build a number of artifacts. Reproducibly, of course, we build compiled queries, we build a dispatcher. We also build evaluation scripts, and we build these into packages that can be deployed on different hosts and the build hosts. Usually you may build on your university servers, or you may build on your laptop, but you measure then in the cloud. You measure on System 390 somewhere in North Romania. You measure on embedded devices like this. That's what we do. And then you generate results, and these results then either give you directly charts, or you feed the results back into the container and use that to reproducibly post-process your data. But the overall goal is to have this single-shot solution. You push a button, everything that you have is rebuilt. It doesn't matter if it's 2021, it doesn't matter if it's 2057. As long as you can still simulate an x86 platform, you should be good, and that's basically what reproducibility is about. Good. Let's move on to another example. How did we do that? Again, we're not going to discuss. You should be seeing now my favorite editor with a lot of tabs on, with the Docker file that we built specifically for this tutorial. I'll just walk you briefly through it. It should be all pretty well documented, which is also a big aspect of reproducibility, because you always need to prepare your artifacts in a way that people who do not know you, who may be thousands of kilometers away from you, who cannot hear you, who don't want to talk to you, must be able to rebuild that. And just out of interest, little target audience check. Who of you has worked with Docker before? Could you please raise your virtual hands? Or the green thing, or...
One hand raised, one green, 3 hands.
So I see a clear preference for hands over green check marks.
It is fine.
Okay, but that's actually not so many, so let's spend a little more time probably on that. I see Sasha Sheik is the most expert Zoom user who can raise both the hand and the green button. Very good. So usually most of you will probably do their research on some Linux platform or another, measure, do compile in the cloud, compile on the server, whatnot, and there you install a distribution, and then you run apt-get in your daily work until you have all packages that you need, compile your code, do your measurements, and so on. And what Docker does is create a virtual machine that's built from scratch from a distribution like Ubuntu 18.04. We deliberately chose a long-term supported distribution. So 18.04 gives us 5 years of support from Canonical itself. So we have a very reliable base platform in the first place. And it also has a number of other advantages to use not the latest and greatest platforms that we cannot discuss here for time reasons, but that's something we are happy to do anytime afterwards. Then you tell Docker how to set up your environment, which commands to run initially. So we do add a number of packages that we need for our research. Basically, we need curl to get stuff. We need Beaver for LaTeX. We need a lot of packages from GNU-R because we use that to generate charts, to post-process data. We do need an editor, of course. We do need Git to pull in dependencies and many other things. TickleDev, that's specifically for SQLite because it uses lots of Tickle, but you come up with everything you need, pull that in, and once that's here, it won't change anymore. So that's the first part of the repository, or Docker file. Then we build a directory structure. Not going to discuss that much now. You can look that up in Stefan Manigold's tutorial, how to design directory structures so that people can understand it and that you distribute everything well. Then we pull in our own dependencies, so our fork of SQLite that comes from GitHub. Then we compile the whole SQLite thing. Then here we build our latency measuring tool, then we build extensions and so on. And what's most important, in the end, we pull in queries and input data from the repository. So what the thing looks like when you clone it from GitHub is like that. You have a Docker file. That's what we're looking at. You have queries, polite and impolite ones. So for instance, queries.polite. You see we have all the TPCH queries that you're very familiar with. So that's the impolite the polite version. Sorry, it says please select nicely. We have a number of scripts that do prepare TPCH data, that dispatch measurements, that dispatch a full set of measurements. I'm coming to that in a second. That's all pulled into the Docker container and then augmented by own extensions and so on. And what comes out of that Docker container is, I'm not going to build that completely now. So we could now go ahead and say Docker build for ICDE 2021, what's in the current directory, so the Docker file that's here. Then Docker will go ahead, create a base image of Ubuntu, pull in all the dependencies, compile stuff, blah, blah, blah. Of course, we've made sure that runs reproducibly. So every time you run that command, you get reproducible binaries. But what do we do now with these binaries? Let me switch into the container. I've already pre-built things. So you see, I'm now not on my host anymore. I'm inside a container. I'm inside the container that has the directory structure, that has the TPCH data generator, that has the dispatcher scripts, and so on. And it has a deliverable tar.bz2. That's if we look into that tarball, that contains the SQPolite binary that we built. So that's a shell for SQPolite. We have the latency measurement tool. We have the dispatches. We have input data. In short, we have everything we need to put that tarball. I would now, if I were to perform a real measurement, I would put that tarball that contains binaries that are guaranteed to be identical regardless when I build them, put that on my measuring hosts on the cloud somewhere else, then run the dispatcher, get data, and feed that back into the Docker container. What we can also do is we can prepare data within the Docker container itself. So our measurement process also does not just work on external hosts, it also works internally. Now it's creating some tables, you know that treat. And you see we're already using our SQPolite version. The TPCH generator, for some reason, is very impolite. So SQLite often asks, what was the magic word again? And you should really fix that, because such an impolite data generator can really not be the basis of all research. But having said that, so once we've generated the data, which still takes a very little while, here we go. We can now run measurements via the dual script. I'm not going to discuss that in detail. It's fairly standard. The dual script basically dispatches 2 measurements based on 0.1 gigabytes worth of data in polite mode, scale factor, in polite mode, 25 iterations, can give a label. And the dispatch script itself also does something similar. It uses a standardized directory structure. You can look at that afterwards, measures a number of TPCH queries. And what's also important, includes lots of information about the measuring system. So not just, oh, we measured on a Dell server that was yellow, but we measured on a Dell server that was booted with this and that kernel command line. Kernel command line is very important to reproduce results, because you can boot Linux kernels with various options that massively influence the performance of the measurement. We include the kernel configuration so that people could rebuild the kernel they used for measurements, and so on. There may be other things that you need to ask your systems expert for that. What's more important is, I will now dispatch this measurement. Say I'm measuring on the Docker host. That will run for a while, and we'll leave that running and come back to that after we've done that. Steffi, you may now want to summarize that, I guess.
Yes, so it's this figure just sums it up, what Wolfgang has already told you. So we've come to the point where we've built the artifacts on the Docker container, and what he's now doing in the background is unpacking. He's unpacking the measurement package and then running the experiments in the background. But usually, you don't want to run the experiments in the Docker container itself. You may be afraid of an additional, if ever so slight, overhead. You may want to execute in a platform where you cannot run Docker, where it's not possible.
Like on S390, everyone's favorite platform.
Or you may want to use system configurations that are not available to you when you're in the Docker container. So the idea is to take the measurement package, copy it onto the target platform, unpack it, run the experiments here. We get CSV files, for instance, package them up again, copy that back into the Docker container where you unpack this packet, and then you generate the graphs in the paper from that. The idea here being that you also want this to be reproducible. Maybe it's happened to you if you're writing a LaTeX document in a team where everybody has their own local installation. Sometimes the figures jump around, sometimes the fonts differ. So even there, if you really want to be reproducible up till the very last dot in your PDF, or if you want to make sure all those LaTeX packages are really available there for the long time, you can generate the graphs in paper here.
We cannot tell you how to do that with Microsoft Word, and we don't care. Good. Next hands-on thing, execution. I already started that basically. And you see it's still measuring. Database is complaining, what was the magic word again? Let's probably give that some more time, but actually I've already shown you the hands-on example for the execution. It's a bit of a technical effort to make sure that things are exactly the same in the Docker container and on the measuring host. There's a number of challenges. Usually you would say I built my reproducible binary with every library linked in statically. So I have one single binary that I can execute on every host. You will realize it's not so easy because you cannot properly link the libc statically these days. It's also problematic with other libraries. So there's a number of dependencies that you need to include. It's a bit fiddling around, but once it works, it really pays off itself, because when you've ever done porting work to run measurements on S390, on Power, on embedded systems, non-x86 platforms, you know how much effort that costs everyone. And that's quite simplified when you do it in one central place and properly.
If the experiments are done, we could show the folder structure, but I'm not sure they're not. Oh, they're not done yet.
Let's check. No, they're still running. A lot of that is contributed to the fact that TCP/H is so impolite and that we need to sleep a lot to punish us.
Okay. Meanwhile, we're going to talk about our Git repositories. So remember, we started out with the original SQLite Git repository, and there's a specific commit that's our reproduction base, and we forked from that to build SQPolite. So this is our own sequence of commits, and we can distinguish different commits. There are certain commits, like those marked in red, that might be bug fixes or refactorings that are interesting for the original project. So we carve them such that they're relevant for being brought back into the upstream's project. And it's not just good citizenship to contribute back to the projects that you forked from. It'll also make it easier in the long run to continue working with the latest code from the original project if they have integrated some of your changes. Yet there are also changes that are relevant to our research only. So we're not sure the SQLite maintainers will want to have a SQPolite with delays in it.
As we said, there's not enough love in this world.
Or in the database community.
Or in the database community.
So we also craft certain commits such that they're only interesting for us. We have yet another line of commits where we're building the Pretty Please extension. Remember, that was a UDF, essentially, where...
Go on, I'll fix our beauty light. You will be disappointed that we're not as beautiful as before.
What happened? Okay. So here we have another line of commits in yet another project where we're building the Pretty Please extension that can actually be mapped or run with SQLite just as well as with SQLite. So that's yet another repository and yet another sequence of commits. So this is where we are now. And the question is, how do we package all of this up for the future?
Yeah, and that's especially interesting because usually this beauty light is really annoying.
Okay.
So when we switch from dark to light, it's not our fault. Why we spend so much effort on that is reproducibility has two aspects. One is the purely technical aspect. So we provide you with a Docker image. You can push a button and you can rebuild everything you need. But you're usually not reproducing things for fun. You find some research interesting, you want to build on that research, you want to understand what was going on. And when you think about how usually like I write code, then I don't get it right in the first try and not in the second try, not in the third try. And I have mistakes, I correct these mistakes, I make more mistakes, I change my decisions and so on. So I get lots of commits. That's not what you want. You don't want to document your thought process. You want to present the result of your thought process. And you don't want certain mistakes to appear so later on in the internet that your children ask you, oh, Daddy, or have you always been so stupid? Or did it get worse over time? And that's where Git also offers a lots of possibilities like rebasing, squashing, rewriting, blah, blah, blah. Again, question to the audience, can you please raise your hand if you have ever either rebased commits or squashed commits together? Okay, that's also not too many people actually. Two. So I think it may make time to go a little slower on that. When we look at how we created, for instance, the SQLite please extension. So here you see all the commits that I did. We started with a developmental commit. We build sometimes on Mac. So this fixes a bit in SQLite for Mac, which is something we will submit upstream. Then we tried to please everyone by being polite. You will also see that we have structured commit messages with the signed off, tagged by, and so on tags to establish a trail of responsibility, who did what. Attribution is very important in science, and so we can recommend to do that. It also documents things so that people who later on in 10 years' time read your code understand the rationale behind that. So why we're trying to be polite, because they're simply not pleasing anymore. That's the reason for our research. Then we discovered, okay, now we are trying to please the users of the database with the Pretty Please extension, but then the database becomes sulky because it's always polite to us, but we're not polite to the database. So we came up with the please select statement that we can also be polite to the database. And we did some thinking, so that's where things go wrong. For instance, I thought it would be good to complain every third time someone doesn't say, please, we've stopped being so impolite. And Steffi told me, oh, this is very impolite. So we needed to fix that to what was the magic word again, but not return any results. So we changed our research design here, but that is something we shouldn't show to the public. So this fix-up should actually be in here. It shouldn't appear in the repository, because when I read that 10 years ago, I don't care if we first said, stop being polite, and then said, oh, please be polite. Doesn't matter. Same thing here. We saw that returning invalid results is not good because it doesn't punish enough. Queries are still faster than before because you don't need to do all this nasty computation. So we decided to do the computation, but sleep for 500 milliseconds. Then at some point, I realized that despite my degree in physics, I have no clue about physical values. That's a commit that you don't want to show to your grandchildren because, of course, MuSleep does microsleeps in microseconds, not in milliseconds, and 500,000 microseconds are actually 1 millisecond. So we corrected that. Then I remembered that USleep actually has been deprecated for maybe 20 years, so we should be using NanoSleep. And this is all stuff you don't want people to read in 20 years' time. So how do we correct that? That's where Git comes into play again.
We're not seeing that yet.
Oh, you're not seeing that? You're not seeing my shell?
Now I see. No, not this one.
Oh, great. When I switch tabs, let me see. Do you see that?
No.
Okay, then I need to add that probably as a new share. So now you should be seeing it, right? Okay. Where am I? I'm in the Git repository of the tutorial. I want to go to the Git repository of the SQLite extension. So you see all the history of all my mistakes, where basically not much is about research and much is about doing mistakes. The initial commit that we used to ensure bidirectional friendliness is that one. And so we say we take that commit as a basis. We rebase to that commit. That means we reset our development history back to that commit. And here we now see all the commits that come on top of this ensure bidirectional friendliness. What we want to do is we want to take this fix up commit and merge it with the previous one. We want to avoid getting lost in physical units, and we want to use the API that has been in place during the last 20 years. So we move all these commits up here. Git can then reorder the commits. Now we say I want to keep the first commit, and I want to fix up these commits into the previous commit. So Git will then create one single commit out of that, integrate that change, that change, that change. And now I can be sure that my grandchildren will not complain about me being unable to interpret SI prefixes, but probably about other things. Of course, we don't want to keep these commits twice, so we remove them from here and here. And now I save that thing. Git then goes on to apply the commits again. Apply them on top of each other. Okay, great. Now I have a merge conflict. Let's quickly fix that. That can, of course, happen when you do changes that contradict each other. So I fixed that. I'll not be able to explain in the brevity of time what happens here. Let's hope that resolves things. Great, another merge conflict. Okay, I need to select that. Okay, let me very quickly finish that. That's something that can happen. It shouldn't. So I made a mistake, but so we have basically two versions of the code, and we want to keep that version. Continuing the rebase. Yeah, and that's it. Now it worked. So it can cost you some effort. That wasn't supposed to be happening right now. I should have planned that better probably. But now if we look at the logs, see, I can even use zoom less than do Git rebase.
I don't see that.
Yeah, as I said, I'm as bad with using Gits as with planning rebases. Now you should see the list of commits in its initial form. So ensure bidirectional friendliness to fix up and so on. I reload that, and you see we already have a much clearer history than before. We have less fix up commits and less to think about for people trying to reproduce that work in 20 years time. What I did before is I already created a branch cleanup where I went through all commits, thought about what do I want people to read when they try to reproduce my research, and what is just the thought process. And what we came up with is 4 commits. This developmental one aside, try to please everyone by being polite, ensure bidirectional friendliness, punish naughty users with sleep, so we distinguish between just not returning results and punishing people, and then a final commit to add measurement, the latency measurement code. But this packages up everything what we do conceptually without letting people interact with the thought process of ours that they're not interested in. One final remark, Here we have more tags by commit, so you can really give very fine-grained attributions. The tested by thing, yeah, does, for instance, demonstrate that, but I'm getting non-verbal signals that I need to speed up, which is probably right. Yeah, camera out, camera, so it's not the... Okay, that's interesting because the clock is very near to the camera, so I don't know if that means a look into the camera or look at the clock.
No, it says look into
Great,
the camera.
but that's anyway all I wanted to tell you about rebasing. Again, we need to refer you to the Git manuals to read that up, to train that in detail, but it's also something that's a little more effort in the first run, but you've all had code from other PhD students, from other researchers spread across 270 commits where maybe 5 matter, and you will do your environment and your colleagues a lot of goodness. So I guess my slides are now also not visible because the Zoom is a stupid tool. I hope you're seeing the slides now. No, you don't. Great. Okay, that's the miracles of Zoom screen sharing, because we have multiple screens and the windows always appear on a random window, it seems. Now it's the... Okay, now it's the right window, so now you should be seeing our slides again, and let me move these to full screen. So basically that was this hand-on about self-documenting patches, trade-off responsibilities, squashing, rebasing, rewriting. Of course, just a very quick introduction of what you can do. The details are left as an exercise to the reader.
But either way, you can do much more than just version your code. You can tell creative stories.
Yeah, it's something that takes a bit getting a bit used to, but it's, again, we can say it's definitely worth that. So one thing we promised in the outline that we won't have very much time to discuss is licensing considerations. But what you've seen in the examples that we've shown you is 2 things. The attribution, so these signed off or developer certificate of origin tags that clearly specify who's responsible for code and especially who is copyright holder of that code. And that's something you shouldn't underestimate. Apart from reproducibility, because all the open source codes you mix up need to be compatible with respect to licensing. So there's too many choices to discuss that in detail here, but we'd like to nonetheless remark that you need to answer 2 questions to yourself and to your lawyers at the university. You need to choose a license, which one. And so what we recommend, especially for code that should be used in the long run, that should benefit from any changes that come from other people, and that should not go into commercialization without your without getting anything back, is GPL version 2 only, because that is a so-called copyleft license that's compatible with quite a lot of projects, but that requires everyone, very roughly speaking, who uses your code and makes changes to offer you to return these changes to you, probably only upon request. What you should use to make industry happy and to make legal people happy is the so-called SPDX, SPDX identifiers. These are these days parsed by automated tools that search files for licenses that can tell you, okay, these licenses are compatible, these are incompatible, and also tell you which conditions you need to satisfy to use that license, and that make everyone's life easier. So usually for our projects, we choose for non-trivial stuff GPL version 2, and for trivial stuff like dispatches, we simply use the free software foundations. What's AP? Anything's possible, anything pleases. I don't know what, but that basically allows just do what you like with the code, because it's trivial anyway, but it still documents that this is your express intention. And again, we're using the SpeedX license identifier to make life easier for people. Good, so that's all we wanted to tell you about licensing. And that, of course, also requires some remarks on proprietary components. So we couldn't agree on a single statement. So Steffi, you may start. No, sorry, we couldn't agree on a single statement. I start because my opinion is just don't, and that's it. But Steffi probably has a different one.
It cannot always be avoided in our research community because we do have big commercial players. So if our advice would be, if possible, try not to use them. If you have to use them, at the very least, make sure that you document what you use and how you use it in a way that allows others, if they get access to the same tools, and if they get access to make sure they get the right versions. And of course, also that they have all the information they need to properly configure, for instance, a commercial database management product, so that they, once they acquire a license, can integrate it into your reproduction package.
So the least thing you should do is take the results that you get out of your measurements and publish these in a DOI-safe repository, so that other researchers who are interested in reproducing the results can, if they cannot reproduce the measurement process as such, can at least reproduce the post-processing of the data.
So we've come a long way in this tutorial, and we've now solved two problems. We have a build that's reproducible, and we have results that are reproducible, even if they're not identical. Like we said, there are variations. There are only equivalent results, maybe not identical, but we can reproduce them. There are two more problems to solve, or steps to go. We need to write a paper, and we need to make our artifacts available.
Exactly. I would argue that the actual science is in making the artifacts available and reproducible, and that writing a paper is just marketing for that last step. But probably the research community may not entirely agree with my opinion. Still, we want to minimize efforts for that as much as possible. If we do measurements reproducibly, we would also want to do the evaluation reproducible. And we will also want to allow that for other people. Our goal is to come up, so to do the measurements in the container and then do some extra steps. And then the container spits out a paper like this, with graphs embedded that are generated from the measured values, with the text embedded and so on. And again, that's quite a lot of effort when you set things up, but it's ideal in terms of integration of documentation, paper, and data. You put that all into one table, into one virtual machine, and everyone can fully reproduce the stuff, including the drawings. And that does not just benefit others, it also benefits your research groups, but because again, everyone has had this situation where people work with LaTeX and you have two slightly different tech life distributions, things don't match up, you have two slightly different versions of R and associated packages, and code runs on one instance, not on the other one, and you save all that hassle with that approach. So what did we do to that extent? What we used is, for one thing, GNU-R and ggplot. That may or may not be the first choice in the database community. It doesn't actually matter. You can do the same thing with Python and matplotlib and many other things. Without going into details here, is what we do is we read the results of a measurement identified by labels. So here's a little configurable portion identified by scale factor. And then we automatically read in these data, post-process them, and generate plots from these data. And we do it in a way that we can use these plots interactively. So while we're still doing the research, we can experiment around with different scales, with different types of plots, mixing up data and so on. But we don't want to duplicate that effort. Once we found the optimal representation, we want to put that into a paper and to integrate the LaTeX sources of the paper, because everyone who doesn't write papers in LaTeX is anyway doomed, which I can testify because I recently tried to write a report in Word because I was forced to, and that was not fun. And the generation of the images proper. So to that end, we are using a tool called Knitr, Knitr. Has anyone probably ever heard of that? Please do raise your green thing or thumb or... Has anyone ever heard of Knuth's approach to literate programming? Yeah, doesn't really matter. It's a system that allows us to combine standard LaTeX, as you know it, with elements in a different programming language. In that case, R. So we can equip our document with R portions, and then we can use that document, execute the R code, so that sets up some things to plot, that sources, reads in this plot.r file I've discussed with you before, so that reads in the data, processes the data, blah, blah, blah. Then we have our tech code, and here we have a figure that we generate. So we have a standard begin figure, end figure environment in tech, but instead of saying then \include graphics, blah, 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 we say, here comes our plotting code that generates the throughput code from the data that we just generated. We'd like to have it 8.5 centimeters wide, 6 centimeters large, and so on. And same thing for the other figures. And since the container has now finished doing the measurements, we can also demonstrate you that live. So the command to run the R code in tech is documented on top of this paper.rnw file in the repository. It basically runs knit on the paper. Knit then runs all the code snippets that are in the paper. That now worked so fast because it uses a quite versatile caching system. So it also doesn't cause you much overhead. So you don't need to do that every time. You only need to do that when your plots change or when your data change. And what I get out is a paper.tech file that I compile as usual with PDF LaTeX. That compiles me the paper to PDF. Now I have the paper inside the container. Let me just quickly copy that out.
I don't see.
Oh, you don't see the thing. Wait a second. I need to. Add the terminal to the screen share. So did you see me generating the paper, or was that already invisible?
Yes, that was visible.
Okay, cool, great. So now let's copy. Let's go. Let's copy the paper out of the Docker container. And then let's open the paper. You don't see that. That zoom is really a bit of a bit. So I'm opening the paper I just generated, and I guess I also need to add another window to my screen share, like so. Yeah, and indeed you see what was coming out, including all the tech errors that are still in there because we used an older version of tech that doesn't matter. So you get out a document with the graphs included that would automatically change when you measure data, change when you put in measure data from different systems, and so on, all at the tip of one button or at the tip of some buttons. You could even further automate that process, integrate knitr into LaTeX and so on, but we're not showing that because we want you to understand the steps. And again, that's quite a lot to set up, but once you've done that and you can use our patterns, our examples to do that, it really saves you in the long run much more time than you actually invest upfront. Good, great. So that closes the circle from end-to-end reproduction. Now what's missing is one thing, namely show what you did not just to the publishers, but to the world.
Yes, we need to make our artifacts available. And one platform that allows you to do that is Zenodo. We upload not just our Docker recipes and our results, but also a pre-built version of the Docker image with all the dependencies already included. So in the worst case, you could always take that and move to your island with no internet access.
That's the
and
only bad
reproduce
thing.
from
You
there.
need internet access once, and then the island can be cut off the internet. But once you have this 1.7 gigabyte image, these grow pretty quickly. The image that we produced in this example is more than 3 gigabytes. So you see how many dependencies you're pulling in and how many possibilities for variation you have. But still, once you have that, you're all set.
So what you also get is a document object identifier that you then can pass on and hand out to people and point to. Now, this is from a different paper that we've recently published, but once you've reached this point, you can happily let your PhD student graduate because you no longer depend on the PhD student to run the experiments. Everything you need is there. You could have your laptop stolen, or you could buy a fun new laptop without worrying without worrying that you can no longer continue this work. You're actually in a really, really good space. So not just for the others, but also for yourself.
Yeah, and you also see from 6 views and 5 downloads, that's a typical value for reproduction packages on Zenodo, how much the communities make use of these possibilities. But it's something that will pick up.
But then it's just, this is from mid-March, so
which is also true.
It still has time.
Which is also true, yeah.
It still has time. Okay, so getting closer to the end, what are the benefits versus the costs? Well, we will not lie to you. Reproducibility engineering is a lot of work. And we also must admit that getting the examples ready was quite some work.
I mean, we finished half an hour before the tutorial, so that was...
Don't tell people.
I know, I didn't say that.
Important enablers to reproducibility are testability, making sure your code is testable, because if you do that, you already structure things differently, and automation. And there are also the benefits in for you. It's going to make you long-term. The automation will save you time. It will save your team time. Like I said, you can build stuff even after your PhDs or postdocs have graduated because you still have it there. If the Git messages tell you a good story, you will not need to ask people to rerun and understand what's happened. You can switch to new hardware without worrying that the old experiments cannot no longer be run. And you will no longer have to negotiate with your colleagues where something works for you, but only you and not for them, or the other way around, because everybody has the same development environment. And that's something that I'm starting to become to really appreciate, because you can trust that they have no secret dependencies, or you have no secret dependencies that make things complicated.
Great. If it doesn't work for anyone in the team, then it's probably still faulty, but that's something that the best reproduction automation cannot solve. Overall, we believe that if your work is fully reproducible and fully automatic, it's just the better software. I mean, it's something that's pretty obvious, and that also shows in daily practice. As always, it's a bit of an upfront investment, but I can also really just recommend going that extra mile, because that extra mile will pay off multifolds in the later steps of the process. And that is basically all we wanted to tell you, except that Steffi was supported by the German Research Council. So I guess we need to say that for legal reasons and to attract even more funding. But having 10 minutes left, we would now be open to taking questions from you if there are any. So there's one on the chat. Let me see if we can. Okay, could you please size up the editor a bit and show the tech code again, integrating the plotter? That, of course, we're happy to do. Yeah, I see that's really quite small. So let me. Are you seeing the screen?
Yes.
And can you read now? Wait, let me do it a little bit larger. Can you read now what's in the editor?
Yeah, no, it's great.
That's maybe a bit too large because the lines don't fit anymore. Yeah, 20 seems like a good compromise. So what we have here is just, yeah, great. So I have to set two different fonts, one for LaTeX mode and one for ESS mode, because that uses two modes of Emacs. It has support for editing LaTeX, of course, and it has support for editing R. So we have a very standard LaTeX document, as you encounter in ACM conferences. We include our packages, we define the conference, that's Ikutukuk in Greenland, that's right between Kulusuk and Tasiilaq, say who we are, and then here comes the R part. That says, okay, that's something you run once for setup, that has nothing in that can change, so that's always cached. We don't want to include any outputs of that. You could also include the output of R. Say if you're producing some ASCII output, you could produce tables, whatnot. It's really quite powerful. Here we say we read the data. That's something we explicitly want to cache. And then we have our paper proper, and here comes the plotting code. We say here is something we want to plot with the TIX device. So that doesn't not just generate as a binary image, it generates as TIX code, TeX code that's then integrated into the TeX document back again. We basically use the result of that gen_throughput.plot function. And let me move to plot.r. Here we define how the throughput plot is plotted, regardless if you're familiar with ggplot or not. You see, we specify the plot here, we specify the labels, we specify various other things. We can even make little differences between plot.r in the interactive code and for the paper. For the paper, for instance, I told the system to rotate the axis a little bit. We usually don't want that, but we just want that for the paper, and so on. And once you are familiar with that, again, it's a little bit to get into, but once you're familiar with that, it's a nice source of extra layer, extra errors, and it's also a nice source of saving time once these extra errors are done with. So another comment from Ralph is a remark that reproducible results is an implicit way of documentation, which is something we completely agree with. And even if Docker files are, of course, a recipe of getting your project up and running, that's something you usually pass on from student to student, from master student to master student, from PhD to master student. But when you have your Docker file, you know that these are all steps. You cannot leave anything out because then it simply doesn't work. You can do that easily in a telltale description, handed from generation to generation since ancient times. With the Docker file, you're guaranteed that things really work once they work once. Great. Any more questions or things that we should show with a larger font size or with a more tasteful color combination or whatnot? We would, of course, also fully understand, given that it's close to 10 o'clock at night in most of your time zones, or probably even later. It should be even, no, wait, is it later in Greece or is it earlier? Same time zone in Italy, I think, but in Greece they're 1 hour ahead. No.
Well, I'm not sure.
They're 1 hour behind. 23 o'clock. So Panos, thanks for holding out so long.
We really appreciate it.
We do appreciate, yes. But that means if there's nothing else, thanks, Panos. If there's nothing else, you can approach us anytime. We will in the next couple of days put out a polished version of the repository with everything you need to recook the stuff that we've shown you. And if there are any open questions, as I said, don't hesitate to contact Steffi or me.
Thanks so much for joining. It's been fun to show this. And like Wolfgang says, we're happy to answer questions also afterwards.
Yeah. And thanks, and see you all sometime soon. Bye-bye.
Bye-bye.
Bye-bye.